the recording. So, okay, I need to explain in quick detail. So dipole and dipole moment. So dipole is any system of charge is said to be dipole if the summation of charge is 0, whereas the independent plus and minus charge is non-zero. Dipole moment is the mathematical calculation which is simply summation of charge with its position vector. So summation of product of charge with its position vector. And then dipole moment may or may not depend on charge choice of origin. If the net charge is 0, then dipole moment remains independent of origin, else dependent. So the same thing I wrote here. And then we had this two examples of H2 and CO2 molecule. And this is the example of polar and non-polar type of molecule and their representation. In chemistry, as I said, the dipole moment will be opposite in representation. It is from plus to minus. And in physics, we take it from the minus to plus. Understood?
Yes, sir.
Now we took a situation where minus charge and plus charge are equal in value, so the net charge is 0 for the system, and we found the answer that it is independent of choice of origin. So you can see the O is not playing any role, isn't it?
Yes, sir.
So again here, coming to this example, we would like to find the dipole moment of a system like this, and we can see the summation of charge here is again 0, right?
Yes, sir.
The summation of charge is here how much? It's 0.
0.
And because summation of charge is 0, it means this will follow the same trend. It will have nothing to do with the choice of origin.
Yes, sir.
So if I ask you what is the dipole moment vector, or simply the magnitude, then you can choose any point as the origin and you can solve, isn't it?
Sir,
Yeah.
like for the calculation of center of mass, can we consider
Yeah.
the center of the positive charge to be
Definitely.
like?
Yes, in the same.
Sir, yes, sir.
So, this
So
will be
and then
plus.
from minus 2.
Yeah.
Yes, sir.
So the distance between them is this much, right?
Yes, sir.
And this you can find easily, no? From simple
Root 3 by 2a. I mean the distance is root 3 by 2a.
So dipole moment is simply either you just add the net positive charge magnitude, which is 2, and the distance is. So the answer is root 3 q, correct?
Yes, sir.
So you can also do by the basic method, the method which you have done, and in fact, you should do this once just for practice. So let's say if I choose this as origin, and this as x-axis, and this as y-axis, then how to write the dipole moment of the system?
You first find the x component, then the y component, and
Yeah, so you can just add the vector, position vector, right, for everyone.
yes, sir.
Yeah.
For the position vector for both x component and y component of 2q minus 2q is 0.
Correct. So that's
So
0.
yes, sir. So it will be q into a by 2.
Yeah.
I q into a by 2 I cap plus root 3 by 2 a j cap.
Excellent.
Plus q into a I cap plus 0 j cap.
So the answer will be q into 3 upon 3a by 2 I cap and root 3a by 2 j cap, right?
Yes, sir.
Because we got the two answer. Then the mod you can take as you can take a by 2 also common. So you got under root of 3 square
3
plus.
also we can take common.
Yeah, actually you can take. So you get the answer. Root 3. Yes, actually you can take. That's a right way of doing it. Okay.
Okay, sir.
So now let's do the next question. So let's say this is a comma 0. This is 2a comma 0. This is minus a comma 0. This is minus 2a comma 0. Same is 0 comma a, then 2a minus a and minus 2. So everything is clearly mentioned here. And now we have charges. Let's say we have plus q, and then we have plus q here. Then we have minus 2q plus 2. Yeah. So there are four charges. So what is the dipole moment of system? You can find the value also, direction also.
So I speak something?
Oh yeah, I was saying something. Not audible to you?
Sir, now you're audible, sir. So did you speak something after telling me to find the dipole moment?
Yeah, yeah. Am I audible to you now?
Yes, sir.
Yes. So now these are four charges kept at these four locations, and we are supposed to find the dipole moment. So you can solve in vector form, and then you can convert it into scalar, or you can do it directly. But it's good to know both methods. Okay.
Okay, sir.
Okay.
So
Yeah.
I'm getting 2QA into I cap plus 3 J cap as the answer. Sir.
2QA into 3 I cap.
So I cap plus 3 J cap.
I just note I made a mistake here. Plus Q and minus Q. Oh, ho, ho. Hmm. Sorry.
It's for zero net charge, sir.
Yeah. It's minus. Now you can change the answer.
Yes, sir. So 6QA into I cap plus J cap.
Okay, so 6QA into.
I cap plus J cap, sir.
Okay. So yeah, that seems to be correct only. So I think this is the first dipole, like this. And if I join this to the second one, right?
Yes, sir.
And luckily both are parallel, right?
Yes, sir.
If I call this as P1, this is P2, they will add up. Correct? And
Yes, sir.
they will not just add up, they will add up value wise also. And we can see the separation is root 2. Q into root 2, so 2 root 2.
Yes, sir.
So
6
the
root
answer.
2 QA.
So you can see both are same answer, right?
Yes, sir.
All right. Now the dipole moment is not only limited to the discrete charge, it can be for any other charge distribution as well. So for example, if we have a so if we have a charge which is like a plus charge on a semi circular ring, and a charge is kept at the center of curvature that is origin, and I'm supposed to find the dipole moment of such system.
Sir, will it be QR sine theta? Integration.
So Q into
Sir,
DQ
like
into yeah,
dq into r sine theta, and we will integrate it from 0 to pi.
like this, dp equals to dq r center into what I have written.
Sir, the horizontal component will get cancelled out, right, sir?
Right, excellent. So yeah, that getting the vertical component, which is correct only. So dp we can attach. So the negative charge will have zero answer because it's only point charge at origin. So yeah, the contribution is 0. So we are supposed to write only for the the capital Q. So we can move theta and cut digital, right?
Yes, sir.
So this will be the dq into r sin theta. All right. Then dq Canada is lambda r d theta. Correct?
Yes, sir.
So now we can integrate, right?
Yes, sir.
Lambda r square sin theta d theta into j square. And theta will go from 0 to pi. Okay.
Okay.
So this turns out to be how much? 1. Sorry, 2, na? Sin will give 2. This. And then you can write lambda question q by pi r. So this is nothing but the q into 2 r pi, which is the center of charge actually of plus charge, isn't it?
Yes, sir.
So you, we can do directly because we know the center of charge is here,
Yes, sir.
and the answer is 2 r by pi. So we can directly add the answer q minus q into 2 r pi. But it's
Yes,
good
sir.
that you have done this method. That's really good. So if you know the basic, you can actually do it for any kind of charge distribution. So that's also possible. Okay. So let's say if I ask you this simple question, in which so let's say the lambda is given by lambda not cos theta. So this is the charge distribution, and r is the radius. So find the dipole moment of such system.
Okay, sir.
Yeah, so try this out. It's really nice.
Okay, sir. So,
Yes.
uh, sorry, just a second, sir. I'll just check for the x component also. Sorry,
Yeah. You need to think of both the components because you don't know about the distribution, right?
yes, sir.
In fact, the y component will be 0 only. You can check.
Oh,
So you need to remember what is the graph of sine theta? Sorry, cos theta. Just plot the graph first.
so cos theta will be symmetrical about y-axis.
Exactly. That's the takeaway. So because it is symmetrical, so both the quadrants will have similar distribution, right?
Yes, sir.
but
So, yes, sir.
but okay, the cos is negative on the left side, no? So this is the negative value, no? This is negative, this is positive, right?
Yes,
So
sir.
charge on this side will be positive. Something like this. So
Yes, sir.
center of charge will be somewhere here. I don't know where, and same here. So you will get the horizontal component of dipole moment for sure.
Yes, sir.
So either you just find the x component or you find the x and y. So when you're not sure about the distribution, it's good to go with the both component of vector because you don't know which one will give the answer. Understood?
Yes, sir.
So try this out. Now this is not very difficult.
Yes, sir. So,
Yes.
so inside the function, I am getting the, I mean, like inside the integration, I'm getting 2 theta as the, like sine 2 theta as the
Integration.
values. Yes, sir.
Yeah, so sine 2 theta is minus cos 2 theta by 2.
Sir, no, sir. Like while applying limits, we have to do it from
No,
0 to pi by 2, sir.
no, limit is from, see, you have to cover the ring. So limit is going to be 0 to 5 only. Limit
So,
is not,
but then inside it's
it doesn't matter.
in 2 theta.
It doesn't matter.
Okay, sir. So whatever it is, I have to put 0 to pi only.
Yeah, so see, let me tell you, if you take elementary somewhere here at theta to theta plus d theta, and then the r vector, the position vector of that particle will be r cos theta I cap and r sin theta j cap, right?
Yes, sir.
So by definition, the dipole moment we define as the charge into its position vector, right?
Yes, sir.
So we are trying to find the dipole moment from the given origin. Also, you can choose whatever value you want because the sum is 0 only. But anyway, that's the only convenient choice of origin. And dq we can write as lambda r at theta, right?
Yes, sir.
So what we get is lambda r square cos theta d theta I cap plus lambda r square sin theta d theta j cap. And now we are supposed to substitute the lambda value as well, right? Which is lambda not cos square theta d theta plus lambda r square and sin theta cos theta d theta j cap, correct?
Yes, sir.
So this is like a lambda not r square cos square theta d theta I cap plus lambda not r square. Let's call sin 2 theta by 2. So we need to integrate both what we can see clearly from 0 to pi. The sin 2 theta will be 0
Yes, sir.
because the time period of the periodicity of sin 2 theta is pi only.
Yes, sir.
So this is term anyway 0. So the net dipole moment which we'll get is lambda not square integration of cos square theta d theta I cap. I'm writing directly 0. This is 0 to pi. And this we
Okay.
know the answer because this is 1 plus cos 2 theta by 2. You know how to integrate.
Yes, sir.
So can you do this part?
Yes, sir.
All right, go ahead.
So I'm getting lambda not pi r square by 2, sir.
Okay. So yeah, because the answer is pi by 2, no?
Yes, sir.
So the answer is correct. The p turns out to be lambda not r square of the pi by 2. It's okay. It looks nice. It is like the area of the circle. That's a very nice answer.
Yes, sir.
The half area into lambda. But okay, this is not the way to get or even remember. This is just a fluke. Okay, it happened. So
Yes,
dipole
sir.
moment can be asked in a variety of ways, and we should be good with finding the answer.
Oh,
So it is again not only limited to the ring, we can do it for the disk as well. Understand? So
yes, sir.
yeah, we can do it for this. So what else we can do? We can go for the next concept, dipole moment. So the next concept is called electric field due to dipole. Electric field due to dipole. So there are various cases. So first is called axial position or end on position. Second is called equatorial position or also called broadside on position, and C will be in general position. So we will see the three category of problem, and we'll develop the idea of dipole. So what exactly we call dipole? So if we have a system of a positive and negative charge which just fail to coincide, and because they fail to coincide, so if you go at a point here, they will create a very weak electric field. So the plus will create like this and minus will create like this, and the resultant of these two will have some value, maybe something like this. So the whole idea is, when we have a dipole, and if you go really far from the dipole, then it will create a very weak field. And now we are interested in finding those weakly interactive fields that the dipole is able to create. So dipole is a condition in which the D, which is called the charge separation, and the R, that is the position at which we would like to find the field, the R will be much bigger than D, so that we can treat the two charge as a dipole, provided of course the sum is 0. So dipole is a condition, a mathematical condition, but we'll start with just solving problems. So the first part is, the first part you can write as the A category. So we have a just two charge particles. Don't think as a dipole as of now. Just think that you're solving a simple problem of two charge particles. So let's say we have a negative charge here and a plus charge here. D is separation, Q is charge. So dipole moment we can write as QD, numerical value, right?
Yes.
Now on this line joining the charge, that we call axial position. So axial position is the line joining the charge. At this point P, we would like to find the electric field. Understood? Just sorry. So now P is a point on the axis of the dipole. All right. Am I audible to you?
Yes, sir.
And the distance, now we are going to take a distance measurement from the center of the dipole. Like, I mean, it really doesn't matter from where you take, but I'm just calling it center. And the distance of the point P, I'm calling as a small r. So do not think about dipole, think about they are just two charges. So the positive charge will create electric field towards the right, isn't
Yes.
it? And we can call this as E plus, and negative charge will create the field towards left, and we can call it E minus. Okay, and therefore the net electric field at point P will be equals to E plus minus E minus. Okay, because they are in the same they are along the same line, so it's easy to find the resultant, isn't it?
Yes, sir.
So can you solve for the EP part, because this is some calculation which you can do easily. So try doing the calculation. But tell me. So are you doing the calculation?
Yes, sir.
Okay, well.
So, sir, are you able to hear me? So,
Yeah.
sir, I'm getting, sir, in the denominator, I had gotten r square minus d square by 4 whole square. So, can I just, sir, is there
So
any approximation involved?
no, no, no. Right now, no approximation. Just you find the a regular formula, which is
Okay, sir. Sir,
KQ. How much? KQ square. Sorry, KQ upon one
rd
into
by,
two whole square.
yes, sir.
And so the answer will be r square minus d square by 4 whole square into uh,
2rd.
2r. Correct. So the answer that the field will create is this 2KQD upon r square minus into r. Okay.
Yes, sir.
So this will be equals to how much? No, this is the answer. Okay, that's fine. This is the answer. Now, what is dipole? This is the like a general answer. This is not dipole.
So, are you speaking something?
No, no. So now, what is dipole? So dipole is approximation. Okay. So we call it for dipole approximation. For dipole approximation, the position at which you are trying to find the field should be much bigger than the separation between the plus and minus charge. Then we treat as dipole. So dipole means the two charge should be at a relatively very small separation. That's the whole idea. So the system, the center of plus charge and the center of minus charge should be in a very close proximity relative to the position at which you are trying to calculate the field or potential. Then we call dipole approximation. So now you get a new formula. So now you can use the approximation and then you can get a really nice answer. What you can write? 2KQDR upon R power 4. Because we can ignore the D by 2 term compared to the R square, right? Understood?
Yes.
In the sum, in the subtraction, because R is much bigger than D by 2 or D, so we can easily ignore it. Understood?
Yes, sir.
So if you ignore, you get the answer 2KQDR by R power 4, which will make it. So the EP turns out to be 2K and Q into D is called P by definition. So now we call the dipole moment, we use a symbolic dipole moment as P, and you can see the R has become R square used to be for charge, now it is R cube. Now it is very easy to remember because dimensionally one extra D has come, right?
Yes, sir.
So the power of the D must increase to balance the dimension, isn't it?
Yes, sir.
So what we can realize that the electric field due to a point charge is inversely proportional to R square, but the electric field due to the dipole is inversely proportional to R to the power 3. So it will decay more faster than a single charge. And that's the obvious reason because the plus and minus will try to cancel out each other's effect. So the decay is quicker than the decay which would have been possible in case of a single point charge. It is clear?
Sir, DQ?
Decay means decay, the loss of field, the strength of field. Okay, you got confused. In decay is not certain. Decay means like the how fast the strength is decreasing with the distance.
Oh, okay, sir.
Which means if I plot the graph uh, on a relative basis, and if I plot the graph for the E versus R, so I may get a graph like this. I may get a graph like this. So if this is 1 by R square, then I can say this is 1 by R.
Okay, sir.
The fast decay, understood?
Yes, sir.
Okay. Understood. So now this is the first case. You got the answer for the first case. The next part is how to write in vector form. So in EP, if you want to write EP vector, you can see something here. The dipole moment vector is towards right, correct? And
Yes, sir.
the net electric field is also right.
Yes, sir.
So at point P, the direction are parallel, isn't it?
Yes, sir.
So we can directly say that electric field is always parallel to the P vector. So we can just write as 2K by R cube into P vector. 2K by R cube into P vector. So the electric field at point P, we can write in vector form as 2K by R cube into P vector. And that shows that the E and P will be always parallel on the axial position. Now, what does it mean is that if I represent a dipole by a single arrow, so this is how we represent the dipole as a single vector. So be it any point. So if you have a line, just a minute. So any point on this line, the electric field at every point will be towards right. Understood?
Yes.
And that's also logical because if you draw the lines of force, it will be like this only.
Yes.
And the lines of force which will be on this line is like this one. This is the lines of force. So it will start from plus, will terminate on minus. So the directional field is always parallel to the axis. So that is how we know it also. So a dipole will create a field on the axis along the direction of dipole moment vector. That's obvious, right?
Yes.
All right. So we'll go for the B part, which we call equatorial position, right? So what we mean by equatorial? So we have again two charge particles. And now this is called the bisector, the perpendicular bisector. So perpendicular bisector is called equatorial position. So you divide this into two equal parts and you move along this direction. And the R is from here on. So the R is the length of the from the center of the line joining the charge to the point P. So again, don't think as a dipole, just think as a two charges. Can you find the electrical value at point P? It's a simple question. You can do it, right? Hello?
Hello, sir. Yes,
Yeah.
we're able to do it now.
Oh,
So,
Yes, tell me.
so I'm getting the electric field as KQD by R square plus D square by 4 whole power 3 by 2.
Oh, yeah, that's correct answer only. So this is the right answer. Now, because you got the answer, okay. So you can understand something. So first of all, the plus will create a field like this,
Yes, sir.
but minus will create a field like this, right?
Yes, sir.
So the value, both the value will be same in value, right? E and E. So the resultant will be towards left, right?
Yes, sir.
So if I call this angle as theta, this is also theta.
Yes, sir.
So this is theta, this is also theta. So this is 2 theta, so this is that's why the net field is along the angle bisector, which you can see clearly. Understood?
Yes, sir.
So what we can say that we got EP, AQD, and okay, so we got the answer. So now what we can see that the dipole moment vector is right, but the field is left, so they're exactly anti-parallel, right? So
Yes, sir.
at equatorial position, the field direction is always opposite to the dipole moment vector direction. That is what we have to keep in mind. So for dipole approximation, now we can do it the same method for dipole approximation. What we can do?
D square by 4 will, we can cancel.
Yeah. So for dipole approximation, we can write as R much bigger than D, and therefore this will become EP equals to KQD by RQ, which is simply KP by RQ. And therefore
Yes,
the
sir.
EP vector we can write as now vector we when we add to vector, then we have to put a minus sign
Yes, sir.
because we have realized that they are opposite. Okay.
Yes, sir.
So now these two are very famous answer which we need to in fact remember. And the C part is the in general, right? So in general, what will be the answer? So in this case, we only do for dipole approximation, not for the like not we take some value. So we treat this as a dipole. So they say this is a dipole, and you may call it PE.
Sir,
And the point, yes,
sir, can we like resume the class in about 10 minutes, sir?
yeah, no problem, no problem.
So
Yes.
yes, sir.
So now we are taking the third scenario in which the point will be neither on the axial nor on the equatorial, rather in somewhere in between. So we have the position here, and the line joining the position to the center so this is theta. So this dipole will have two components. One will be, so what we do is we resolve the component itself. So you can take a component of dipole moment here. So if the dipole moment is PE vector, then this component we can attach PE cos theta, correct?
Yes, sir.
Another component will be at a right angle. So what we do is we resolve the dipole into two mutually perpendicular components, and we can call it PE sin theta. Then instead of the dipole, we look for the component and their effect which they can create. So we know that for PE cos theta, the point P automatically becomes the axial position, right?
Yes,
So for PE cos theta, the point P is axial position, and we know that the electric field that it will create is in the same direction as R vector, right? So this we call it ER vector because that's the radial field or the field component along the radial direction. And if you look at the PE sin theta, the point P will behave as equatorial position. And we know that the field at equatorial position is opposite to the dipole moment, right?
yes, sir.
So the field will be like this. And we can call it E theta because this is at in the sense that theta is increasing. So we call it E theta. So to find the electric field, the net value, we are supposed to take the resultant of these two. So this will be equals to EP, and we can easily find the EP vector. So we can write is ER equals to, now ER is due to which vector? ER is due to the PE cos theta. So we have to use the dipole formula, dipole sorry. So this will create the field like this. Now dipole, I mean we have to use the formula for the dipole approximation directly. So the PE cos theta will create how much field? Can we write here? What is ER value?
So is it 2 KPE cos theta by R cube?
Excellent, very good. And so only what will be the E theta value?
KPE sin theta by R cube.
Excellent, very good. So because we know the two components which are mutually perpendicular, so we can find the EP value, net value, we can by under root of square of these two terms. And we can take common as Kp by R cube, will get as a 4 sorry, cos square theta plus sin square theta, right? And you can rewrite as So 4 cos square theta plus sin square theta will become 1 plus 3 cos square theta, because I'm writing sin square as 1 minus cos square. Okay. So this way of writing is also okay. So this is the net value of field. So the things which they will ask you further is finding the alpha angle, which is not very difficult. So can you find the alpha angle?
Yes, sir.
So what will be tan alpha? Tan of alpha will be
So it will be E theta by ER.
excellent. So I'm writing here. So tan theta equals to E.
So tan alpha, right, sir?
Sorry, my bad. And if we substitute the formula which we have, the answer will be tan theta by 2. So the tan of alpha is a really nice answer. It's a tan of theta by 2. And what is theta value? So theta is the angle between the r vector and the p vector. Understood?
Yes.
So theta is angle between r vector and p vector. So if I write p dot r, then can we write this as p e r cos theta, right?
Yes.
Which is like p cos theta into r. So why I'm writing this? There's an intention. So if I look at the ER formula once again, the formula is 2k p cos theta upon r cube, right?
Yes, sir.
This was the answer. This was the answer, right? So this you can write as 2k and p cos theta r by r power 4. That's okay. That's not out. So the ER terms are to be 2k and the upper numerator becomes p dot r, okay, upon r power 4. Understood?
Yes.
So in vector form, we can write as 2k p dot r power 5 into simply not power 5, r power 4 into r cap. Right, like this, we can write like this. Because the ER will have the radial direction, isn't it?
Yes.
Okay. Now, similarly, if I want to write E theta in vector form, so first of all, E theta is how much? So E theta is KPE.
Sin theta by R.
So here we have to be a bit smart. I mean, to solve this, we have to go back to the vector notation. And if I call this as PE, and if I call this as R vector, okay, and let's say extend this line. So if I draw a perpendicular, not like this. In fact, I should draw a perpendicular like this. So if I draw a perpendicular from the PE to this vector, so this vector will be P sin theta, right?
Yes, sir.
This the perpendicular is P cos theta, P sin theta, isn't it?
Yes, sir.
So if I call it O A B, then OA vector we can write as what is OA vector? It is P cos theta into R cap.
Yes.
So AB vector is So from triangle we can write as, if you remember, OA plus AB equals to P vector. I mean OB vector basically,
Yes.
isn't it? So AB vector turns out to be how much? P minus P cos theta into R cap, isn't it?
Yes.
So basically, the P sin theta is so if you want to write it in the vector notation, we know that the E theta will have direction. Okay, I need to go back here, then you can get the answer. So how to write this direction? Because that's very interesting. How to write this direction? E theta vector. Okay. So we know how to write the direction of ER because that's in R vector, R cap. Okay, this is R cap.
Yes.
So okay. So we can write as R vector and okay, I'm trying to write the ER and R. That's okay. So E theta vector will be minus KPE, and direction is also very unique. It's a okay. So we got the direction, right? We got the direction. So this direction is what? This is the direction. Actually, this is the direction. It's a minus BA. So BA vector is how much? Yeah, we got the direction. BA vector will be P cos theta R cap minus P.
Yes.
So E theta will be how much? E theta will be K, and this is nothing but the P sin theta. Understood? This is into E theta. I mean, sorry, like this, the theta direction. So this is the very difficult way of writing the PE sin theta vector. So now we can write as K by R cube, and the remaining we can write as K P cos theta R cap minus P. Is this clear? Difficult. This we can write as, okay, basically from here you can write as E theta vector as Kp sin theta upon R cube into E theta, right?
Yes,
And
sir.
this arrow is E theta, if you remember.
Yes.
So that's why we are getting this answer. So now why we are writing both in vector form? Because now we can write the net value in vector form, EP vector, and that will be ER vector plus E theta vector. So it is very easy to write in scalar form, but it's very difficult to write in vector form. So now we have vector notation, and you can actually write in a vector form as well, and this will be equals to 2k and this we can actually further write in a nice way. So we can write as k upon r cube, and p cos theta we can write as pe dot r upon r into r cap minus pe. That's it. So we can add these two, right? The first two terms, these two terms, isn't it? So let me just multiply this first. Uh, Next page. It's a big calculation. So EP we can write as 2k p dot r upon r power 4 into r cap minus plus k by r cube P R by, okay, now this will become same, P power 4 and then P dot R into R cup, right? This we can multiply these two terms and it looks same. And then last term is K by R cube P. Yeah, understood.
Yes.
So if you add these two terms, what you get is K by R power 4 into, this is 3 na, 3 times P dot R minus K by R cube into P. Understood?
Yes, sir.
So K by R power 4, if I take common, I get 3 times P dot R minus R into P. Like I have to think about something to write here. R, because R power 3 was there, so I put write like this. So how to write this? Okay. And this is simply P vector. This we can write like this also. So I think this is the right, this should be the right answer. Just let me confirm. This is a very famous way of writing. Just a moment. Just a moment. Okay, not getting it here. So I think this should be the right way. So, so this should be this is the right answer, but what I'm missing is a nice way of writing. Maybe something I'm missing here. R is R. Just a minute. Switch on the Okay, so I think this is the right answer, not an issue. This is a vector form of writing this entire equation, which is really cumbersome. But I think the formula which we need to write is for potential, which is easy to write. Okay, so there are certain questions that will be asked to you. That question like find theta for what value of
So I
theta.
have a doubt now.
Yes, tell me.
So here in the form that you wrote, it looks like it's scalar minus a vector.
No, no, no.
So
This is right. You said this is R cap mission, no? R cap.
oh yes, sir.
This is R cap. So actually, this is you can write like this R cap, and the problem is the second term I cannot bring the R cap there. Yeah, this is R cap mission for sure. I missed this part. So now, okay, that's fine. No? K by above 4, and then we have price of P dot R cap minus R. Okay. So coming to the for what value of theta, this is the actually question and example both. For what value of theta, the EP will be perpendicular to the PE vector. So which means EP dot P equals to 0.
Yes, sir.
So okay, let's try this. I mean, I'm doing for the first time in vector form, but this is very easy in terms of scalar. So in vector form, what you can write is K by R power 4 3 PE dot R cap minus RPE dot P. So if you do so, you will get K by R power 4 is cancelled out. So what you get is 3 P dot R. Now R dot P will be what? So it's a component of P along the R value, which is P cos theta, right?
Yes, sir. Yes, sir.
And P dot P is what? P square,
Yes, sir.
which is equal to 0. So, and then we can also write as 3 P dot R is P cos theta into P
Yes, sir.
cos theta, which is square minus. So what we get here is
There is an R also, right, sir? P cos squared theta R.
R, right. So R will, okay, R will cancel out. Yeah. So now this R will cancel out, common term. So what you can write is P square is also cancelled. 3 cos square theta, 3 cos theta minus 1 equals to 0.
Yes, sir.
Cos square theta is 1 by 3. So cos theta is 1 by root 3, right?
Yes, sir.
At a value cos inverse 1 by root 3, this is possible, right?
Yes, sir.
This is one way of proving, which is actually correct answer. So let's prove it scalar form. Like so in scalar form, what we can write? So we know that. Let me draw this diagram first, then you can understand. So this is R. So this is theta. And what we realize that ER is like this and E theta is like this, correct?
Yes, sir.
And the resultant of these two, we call it EP, right? Something like this.
Yes, sir.
If the whole idea is what is the angle between this line, which I can extend, and this line. So the question is, what is the angle between these two vectors, right? This angle.
Yes,
So
sir.
let's call it phi. So this is alpha. Then we write theta equals to phi equals to theta plus alpha.
Yes, sir.
So this is the in general answer. So we can say the question is for what value of theta, the phi is 90. So if I put phi equals to 90 degree, then theta plus alpha must be 90.
Yes, sir.
Alpha must be 90 minus theta.
Yes, sir.
So tan alpha will be cot theta.
Yes, sir.
But tan alpha we know itself is tan theta by 2.
Yes, sir.
So tan square theta will be 2. So tan theta will be root 2. So theta is tan inverse root 2. Now earlier our answer was in terms of cos theta. So let's calculate from here. If tan theta is root 2 by 1, what is cos theta then? 1 by root 3.
By root 3. Yes,
See,
sir.
our answer is correct, which means the formula that we had was perfectly correct. Understood?
Yes, sir.
So there are two ways of solving. Of course, if we will go with the scalar method. The vector is really cumbersome to derive and remember. But nevertheless, I mean, that was the formula I just wanted to give. I don't teach to every student, but I believe that you can understand this. It's not very difficult.
Yes, sir.
So you can just practice for some time, and that's it.
Oh,
Okay, so we are done with the field part, like how to find the field of a dipole. Okay. So the next
yes, sir.
concept is called the potential part. Potential due to dipole. That's very simple. So again, you have to start with the same method. Like assume there is nothing like a dipole. Just we have two charges, q and minus q. So now we have two charges plus q and minus q, and the d is a separation, and the point p is here. So we started with the similar kind of assumptions. So from center of this charge, we have a point P, which is called r distance away, and this is the axial position. So the answer is the A part is again at axial position. So you need to remember that I mean it's, potential is a scalar value. So we just need to add the algebraic value, and we know that in case of calculation of potential, the sign of charge will matter. So plus charge will have positive contribution and negative will have negative contribution. So what is the potential at P? Tell me. So first do the regular thing, then we start with the approximation. You got two answers. Right?
okay, sir. So I'll be getting two answers.
No, no. You first write the normal answer, like without any approximation. Then use the dipole approximation later on.
Okay, sir. So,
What's the answer?
yes, sir. So I'm getting k cube d by r square minus d square by 4.
And for dipole approximation, how much is VP?
So k cube d by r square.
So it is obviously earlier we used to have KQ by R. Now D has come in the numerator, so the dimension will match. So KP by R square. Okay. And the B part is pretty easy. At equatorial position, we'll get nothing, right? Because the plus minus will contribute equally and will
Yes,
make
sir.
it zero.
Yes, sir.
So in fact, we
Equal
can also think
distance.
about, yeah, equality. We can think of the equatorial plane also, not just line. So even if you think of a plane passing through the middle,
So for the
over this,
entire plane, if any point is
ah,
there, then it will be
right.
equidistant.
So a entire plane will be the equipotential or zero potential plane.
Yes, sir.
Zero potential plane. So we call it just zero. Okay. So now the obvious question is the third part will be, so what's the in general answer, right?
Yes.
So we always keep the general thing for the dipole approximation case only. We don't do it for the regular value. So if that is the case, then you will do the same trick. So same trick is you resolve it, and the component will which will not contribute is this component, the yellow one, and the blue will contribute, right?
Yes, sir.
So the P cos theta will contribute, and the P sin theta will contribute nothing, so that's equatorial position. So we can say VP equals to how much? K P cos theta by R square, right?
Yes, sir.
And therefore the VP turns out to be okay, KPE dot R upon R, something like this. You can also write like this, isn't it?
Yes, sir.
So we can also write in like a vector notation like this, and therefore I think we can also go for the no. So because we have VP equals to KP cos theta by R square, this is like a polar system. So in polar system, we can write as the radial component will be minus del VP by del R, the reverse derivation we're doing. Because this is easy to write. Now we can always write the potential in an easier manner. Finding the electric field is slightly difficult. So potential is the easy way. So you start with potential. Now you differentiate the R, the radial value. So if you differentiate the equation 1 with respect to R, it will become minus Kp e cos theta by RQ, isn't it?
Yes, sir.
And it will become plus answer because minus of minus become plus, isn't it? 2 will also minus 2 by RQ, right?
Yes, sir.
So you can see that we got the answer very directly, very quickly, and that's a minus sign is also saying that the answer will be along the R direction because this plus answer. Okay, and similarly, in the polar system, if you wish to find the E theta, the way of writing is minus del V by R d theta. So you can say R into del theta. Understood? So minus 1 by R. Is this clear? No, correct. No. So it's like this. So for a given point P, there are two ways to move, right? Either move like this is called the radial direction, or you can move like this. This is called theta direction. If this is R, this is theta or d theta. So electric field in the radial direction is we can write as minus del B by del R. So you move along the R. So how to find E theta? So how much you move along this direction? What is this length? Length is how much? R d theta.
Yes, sir.
That's why we write R d theta. I'm just writing del. So the E theta will have this formula. Understood? We are writing distance, not the angle. So
Yes.
the R is coming because we are writing distance, not the angle. So if you differentiate this, you will answer -1 by R into K by R square into P. The cos theta you can differentiate as minus sin. So E theta turns out to how much? Kp. You can see something interesting that we got both the answers in the potential very easily. So whenever potential is given, you can always apply the radial component and the angular component, if any, to get the answer. Understood?
Yes, sir.
All right. So after knowing the potential and all, the next concept that we need to learn is called the potential of a dipole kept in external electric field. And this I will continue in the next lecture. Okay. So I have another lecture coming up in a few minutes. So now in the next lecture we will be able to finish everything and the entire dipole concept will be over. And now you will be free to solve any question, every question. Okay.
Okay, sir.
So we'll finish it, and then after that I will start capacitors, hopefully. Okay.
Yes,
All right.
sir. Okay, sir.
Good night. Take care.
Good night, sir. Thank you, sir. Bye, sir.
And let me know if the recordings are left. I mean, generally I forget, so don't give me after a long time. Keep on reminding me as soon as possible. Okay.
Okay, sir. Yes, sir. I'll check it and remind you, sir.
Yeah. Okay. Thank you. Good night.
Good night.